Hello friends, welcome in this video session of steady state conduction through composite of subject heat transfer. My name is Mr. S.V. Kumbar, Assistant Professor, Sharad Institute of Technology, College of Engineering, Kedra, Ichalkaranchi. So these are the contents of today's video lecture. So first, composites, introduction and its application, derivation of heat conduction through composite wall, thermal resistance, numerical based on thermal resistance, overall heat transfer coefficient, numerical based on overall heat transfer coefficient, heat conduction through a composite cylinder, and numerical based on it. So we will start with composite material. Generally we call it as composite. So what is a composite material? A composite material is a material made from two or more constituent with significantly different physical or chemical properties that when combined produce a material with characteristic different from individual component. Composite material is also shortened as composite. Generally we call it as composite as it is. So typical engineered composite materials are: first, reinforced concrete and masonry. Generally we call RCC, reinforced concrete cement. Generally wall is made up of brick as well as cement concrete layer. So these are the two different material. When it is combined together, it forms a composite material. Composite wood such as plywood. In plywood there are different layers, so we call it as composite. Reinforced plastic such as fiber reinforced polymers or fiberglass. This is one of the composite which is generally used in most of the mechanical engineering application. Ceramic matrix composite, that is composite ceramic and metal matrices. Metal matrix composite and other advanced composite materials. The composite materials are generally used for building bridges and structure such as boat hulls, swimming pool panel, racing car bodies, shower stall, bathtubs, storage tank, imitation granite and culture marble sinks and countertops. So this is all about composite material. In day-to-day life activities, we also use composite materials. Now it's a time to take a derivation of heat conduction through a composite wall. Now consider a composite wall. Now here three different layers are shown which are made up of different material A, B, C. These are the different materials and these are combined together to form a single unit. Now let's say T1 is the temperature of left hand side wall and T4 is the temperature of right hand side wall. Let's say Ka, Kb and Kc, these are the thermal conductivity of material ABC. Let's say Ba, Bb, Bc, which are shown here. Ba, Bb and Bc, these are the thickness of slab or composite material ABC. Let's say T2 and T3, these are the intermediate temperature. T2 is here, T3 is here. Since the quantity of heat transmitted per unit area per unit time through slab is same, then we can write Q is equal to Ka A T1 minus T2. Remember, this is the amount of heat transmitted through body A, that is material A. So the amount of heat transmitted through material A is given as Ka, that is the thermal conductivity of A is the area of A, T1 minus T2. This is T1 minus T2. T2 is the intermediate temperature between A and B, which is equal to Kb. Kb is the thermal conductivity of B. A is the area of B. T2 minus T3. This is the temperature drop of B material divided by Bb, which is the thickness of B, which is equal to Kc, that is thermal conductivity of material C, multiplied by area of C. T3, that is the intermediate temperature between B and C, minus T4 upon BC, and its equivalent electrical circuit is shown here. T1, T2, T3, T4, these are the temperature at appropriate points. RTH, that is thermal resistance of A, RTHB, that is the thermal resistance of B, RTHC, that is thermal resistance of C, which is given by this formulae. So rearranging this equation in previous year, we have just rearrange this. Try to express this equation in terms of T1 minus T2, T2 minus T3, and T3 minus T4. Just rearrange this, we will get T1 minus T2 is equal to Q into BA upon KA into A. T2 minus T3 is equal to Q BB upon KB into A, and T3 minus T4 Q BC KC upon A. I would like to just repeat once again. Just rearrange this equation in terms of T1 minus T2, T2 minus T3, and T3 minus T4. We will get these equation, and after that adding equation 1, 2 and 3. Just add equation 1, 2 and 3. T2, T2 will get eliminate, T3, T3 will get eliminate. So T1 minus T4 will be the addition of right hand side. So Q BA upon KA plus Q BB upon KBA, Q BC upon KCA. So Q is taken outside. Here Q is taken outside. BA upon KA into A plus BB upon KB into A plus BC KC into A. Now just again take A as common from this denominator. We will get QA upon A, and after simplification of this equation we will get Q is equal to T1 minus T4. A is taken common, it will be multiplied here. A into T1 minus T4 divided by BA upon KA plus BB upon KB plus BC upon KC, or rearranging this term T1 minus T4, this A is again taken to denominator. So BA upon KA into A plus BB upon KB into A plus BC upon KC into A, which is nothing but thermal resistance of material A, B and C. This is the summation of thermal resistance of material A, B, C. So Q is equal to T1 minus T4 thermal resistance of A plus thermal resistance of B plus thermal resistance of C. Now in this problem, in this derivation, there are only three layers A, B, C. But if the composite wall consists of n slabs per layer, then this equation is generally represented as Q is equal to T1 minus Tn plus 1 divided by here summation of B upon Ka from 1 to n. Now, in order to solve more complex problems involving both series and parallel, now if you observe carefully, material A, B, C are in series. That's why thermal resistance A, B, C, these are connected in series. Now in this case, if a material is connected in series or parallel, then those resistance can be added or here by using parallel and series law of resistor. So the electrical analogy may be used, that is Q is equal to delta T overall divided by summation of RTH. Now here material A is connected with B and C, but B and C are parallel, right? Material B and C, these are different material which are connected in parallel, which is connected in with series A and D. Similarly E, F, G, these are the materials which are connected in parallel, and heat is transmitted through such complex problem. Now here its equivalent circuit is shown here. First of all, thermal resistance of A. Thermal resistance of A, this A is connected with series with B and C, but B and C are in parallel. So thermal resistance of B and thermal resistance of C has to be connected in parallel, and its equivalent resistance is taken into consideration for solving this circuit. Similarly, Kd, that is thermal resistance of D material, and EFG, these are connected in parallel. So here also thermal resistance of EFG, these are shown in parallel. Now again its equivalent thermal resistance is calculated first, then it is replaced by its equivalent resistance in order to solve such a complex problem. The next point is thermal contact resistance. In composite multilayer wall, the calculation of heat flow are made on certain assumptions, and these assumptions are the contact between adjacent layer is perfect. Now, when A and B are connected, this junction between A and B must be perfect. That was the first assumption. At the interface, there is no fall of temperature, and at the interface the temperature is continuous, although there is a discontinuity in the temperature gradient. But in real there is a gap between A and B or B and C. Sometimes air may also present in between A and B, or at some edges the part is discontinuous, means it is not touching to each other. So in that case, here in real system, however, due to surface roughness, void spaces, that is air gap, which is present between the contact surfaces, and thus there is not a single plane of contact, which means that there are area available for the flow of heat at the interface. In between A and B junction, or in between B and C junction, due to this reduced area and presence of air, a large resistance of heat flow through an interface occurs. And this resistance because of air is known as thermal contact resistance. Now, in this figure, A and B, instead of temperature T2, temperature drop occurs from T2 to T3, means A composite material left hand side is kept at T1, and at the junction the temperature has to be T2, but because of presence of air, here there is a temperature drop from T2 to T3. Similarly, at the junction of B and C, only T3 has to be there, but because of air gap which is present between B and C, the temperature drop T4 and T5 is present, right? Now this composite wall is having air gap or void at the junction, that's why there is a temperature drop from T2 to T3 and T4 to T5 occurs. The contact resistance RTHAB, that is thermal contact resistance between AB, is given as T2 minus T3. T2 will be the highest temperature, T3 will be the lowest temperature. T2 minus T3 divided by the heat transfer rate divided by area through which it is flowing. Similarly, thermal contact resistance between B and C junction is given as T4 minus T5 divided by Q upon A. So we will solve one numerical based on this. We will read problem first. The insulation board of air conditioning purpose are made of 3 layers, middle being of packed glass 10 centimeter thick, whose thermal conductivity K is equal to 0.02 watt per meter degree centigrade, and the sides are made up of plywood of each of 2 centimeter thickness. K is equal to 0.12 watt per meter degree centigrade. They are glued with each other. Determine the heat flow per meter square area if one surface is at 35 degrees centigrade and other surface is at 20 degrees centigrade. Neglect the resistance of glue. So in earlier video lecture also I suggested to draw a simple figure for this problem. Again we will read the problem. The insulation board of air conditioning purpose are made of 3 layers. There are 3 different layers, out of which middle layer is packed grass of 10 centimeter and outer two one of plywood which are of 2 centimeter thick. So this would be the diagram. Middle one is 10 centimeter, so here middle layer is shown 10 centimeter, and outer one A and C, these are of plywood which is of 2 centimeter each, right? Next, these are glued together, and if one surface, that is T1, is 35 degrees centigrade and here T4 is 20 degrees centigrade, we have to calculate heat flow per meter square area, means area A is equal to 1 meter square, Q upon A is nothing but heat flux. We have to determine heat flux. So what is the given data here? Thickness of each plywood BA and BC is 2 centimeter, means 0.02 meter. The thickness of grass layer, it is 10 centimeter, that is 0.1 meter. Thermal conductivity of Ka Kc is equal to 0.12 watt per meter degree centigrade, and thermal conductivity of grass is 0.02 watt per meter degree centigrade. Temperature T1 35 degrees centigrade, temperature T4 20 degrees centigrade. Now here heat flow per meter square area, that is heat flux, this A is taken to left hand side, so Q upon A, heat flow per meter area is known as heat flux, that is T1 minus T4, T1 minus T4 upon RTH, that is thermal resistance of A plus thermal resistance of B plus thermal resistance of C, which is equal to thermal resistance of A is given as BA upon Ka into A plus thermal resistance of B is given as BB upon KB into A plus thermal resistance of C is given as BC upon Kc into A. So temperatures are given. So convert these temperature in Kelvin. Even if you don't convert, as it is a difference, 273 will get cancelled. You will get the same answer upon BA is 2 centimeter, 0.02 divided by Ka is 0.12 right here into 1, because area is not given. Per meter square means area is 1 plus 0.1, that is the thickness of grass, divided by 0.02, that is thermal conductivity of grass, into 1, area is not given. Per meter square area means A is equal to 1 into 0.02, 0.12 into 1. So after solving this, we will get heat flux, that is heat transfer per meter square area, as 2.81 watt per meter square, right? Next, overall heat transfer coefficient. Now, while dealing with problems of fluid to fluid heat transfer across metal boundary, it is usually adapted to overall heat transfer coefficient U, which gives heat transmitted per unit area per unit time degree temperature difference, the bulk fluid of each material. Now, if the generally heat transfer takes place by two modes of heat transfer, first convection, then by conduction, generally overall heat transfer coefficient comes into picture. You consider one wall which is having thickness as B, K is equal to thermal conductivity of wall material, T1 is the temperature of left hand side of this wall, T2 is the temperature of right hand side of the wall. Now if air is present on both the side or any gas is present on both the side, so let's say if hot fluid is present here, either air or any gas or water, so THF is the temperature of hot fluid, THF is the temperature of hot fluid, TCF is the temperature of cold fluid, and HHF, that is the heat transfer coefficient from hot fluid to metal surface, and HCF, here HCF is the heat transfer coefficient from metal surface to cold fluid. Now if you draw its equivalent circuit, heat will be transferred from this hot gas to metal by convection, then from T1 to T2 by conduction, and from this T2 to TCF by convection. Now two modes of heat transfer comes into picture. First, the heat transfer from hot fluid to metal surface by convection, then within the metal by conduction. From T1 to T2 heat transfer takes place by conduction, and from this metal surface to ambient air by convection. So three resistors are shown. First one is the convective resistance at inner side, that is to hot fluid, then thermal conduction resistance B upon Ka, and again convective heat transfer resistance to cold film temperature, right? Now again, the equation of heat flow through fluid metal surface is given as Q is equal to HHF A THF minus T1. This is the amount of heat convected from hot fluid to metal. Q is equal to Ka T1 minus T2 upon B, which is the amount of heat transmitted through metal, and Q is equal to HCF A T2 minus TCF. This is the amount of heat convected through air which is in touch with hot metal. So just rearranging this term, so THF minus T1, this HHFA is taken here, it will become Q upon HHFA. Similarly, this T1 minus T2, this B is multiplied by here, Q into B upon Ka. Similarly, this T2 minus TCF is kept, this HCFA is taken to left hand side. So by rearranging this equation, we will get, now again adding equation, this plus this, minus T1 plus T1 will get cancelled, minus T2 plus T2 will get cancelled. So what will remain? THF minus TCF, which is equal to addition of right hand side. Again Q is common, Q is taken outside, into bracket 1 upon HHF into A plus B upon Ka plus 1 upon HCF into A. So again solve for Q, take this term to left hand side, it will become Q is equal to A THF minus TCF divided by 1 upon HF plus B upon K plus 1 upon HCF. Now if U is the overall heat transfer coefficient, then this equation can be written as Q is equal to UA into THF minus TCF, which is equal to A THF minus TCF upon 1 upon HHF plus B upon K plus 1 upon HCF, where U, that is overall heat transfer coefficient, is 1 upon HHF plus B upon K plus 1 upon HCF. This is known as overall heat transfer coefficient. Now generally, if heat transfer takes place by more than 2 modes, then generally we consider this U, and this U is 1 upon summation of thermal resistance. So don't forget to calculate summation of, that is thermal resistance. We will solve one numerical based on overall heat transfer coefficient. Read this problem. A mild steel tank of wall thickness 12 mm contains water at 95 degrees centigrade. The thermal conductivity of mild steel is 50 watt per meter degree centigrade, and the heat transfer coefficient for the inside and outside tank are 2850 and 10 watt per meter square degree centigrade respectively. If the atmospheric temperature is 15 degrees centigrade, calculate the rate of heat loss per meter square of tank and the temperature of outside surface of tank. These are the two questions. As I said earlier, try to draw its small figure. So figure is not given. A mild steel, this is mild steel tank of wall 12 mm thickness. So B is given as 12 mm, convert it in meter, contains water at 95 degrees centigrade. At left side, hot water is kept at 95 degrees centigrade. The thermal conductivity of mild steel is 50 watt per meter degree centigrade. Its thermal conductivity is given, and heat transfer coefficient for inside and outside. This is inside part and this is outside part. So HF is given as 2850 and HCF is given as 10 watt per meter degree centigrade. If the atmospheric temperature is 15 degrees centigrade, atmospheric temperature is 15 degrees centigrade, that is the TCF, we have to calculate Q. So this is the method to draw rate of heat loss per meter square is given as Q is equal to UA THF minus TCF, where U is the thermal that is conductive resistance plus convective resistance. So 1 upon U is equal to 1 upon HHF plus B upon K plus 1 upon HHF. HHF is given as 2850, put it. B is 12, it is in meter, that is 0.012 divided by 50, that is thermal conductivity, plus 1 upon 10. We will get the value of U as 9.94 watt per meter square degree centigrade. Substitute the value of U in this equation, we will get Q is equal to 9.94 into area is not given, but heat loss per meter square area is given. So A is equal to 1 into 95, that is THF, minus TCF. So the heat transfer per unit area is 795 watt per meter square. The next question is the temperature of outside surface of tank, means we have to calculate T2. Now just consider the heat transfer from this metal to air by convection, which is given as Q is equal to HCF T2 minus TCF into area. So Q is known to us, that is 795.2, HCF which is given as 10, area is 1, T2 that we have to determine, and TCF the value is 15 degree centigrade. So solve this, we will get T2 as 94.52 degree centigrade. Now heat conduction through composite cylinder. Now in earlier problem we have seen if a metal is in contact with hot fluid, then convective thermal resistance also taken into consideration, and after that we have considered overall heat transfer coefficient. Very similarly, in such problem, if it is a composite material, here two different cylinders are used, A and B, which is having thermal conductivity K1 K2, and inside of first cylinder a hot fluid is flowing, and if the heat transferred from this hot fluid to atmosphere, then in such problem equivalent circuit is drawn here. R1 is the thermal convective resistance, R2 is conductive thermal resistance, R3 is again thermal conductive resistance of second material, and R4 is convective thermal resistance. So R1 is calculated as 1 upon H1 into A1. Now A1 is considered as 2 pi R1 L1, which is circumferential area of inner cylinder. R2 is ln R2 upon R1 upon 2 pi Lk. This is the heat transferred through first cylinder. Similarly, heat transferred, that is thermal conductive resistance, for second material, R2 is given as ln R3 upon R2 2 pi Lk2, and R4 is 1 upon H2 A2, where A2 is 2 pi R3. R3 is the radius of outermost surface into L, and summation of R1, R2, R3, R4 is taken for calculation. We will solve a numerical, then you will come to understand. Here a standard cast iron pipe, inner diameter 50 mm and outer diameter 55 mm, is insulated with 85% magnesium insulation. K is equal to 0.02 watt per meter degree centigrade. Temperature at interface between pipe and insulation is 300 degrees centigrade. The allowable heat loss through the pipe is 600 watt per meter length, and for safety the temperature of outside surface must not exceed 100 degrees centigrade. Determine the minimum thickness of insulation required and the temperature of inside surface of the pipe assuming its thermal conductivity is 20 degrees centigrade. So try to draw a small figure for this. So this is hatched part is nothing but cast iron pipe A, and its inner and outer diameter is given. So while solving numerical, we will require its radius. Here R1 is given as 50. R1 is given as 50 divided by 2, that is 25. Try to convert it in meter. Outer diameter 55. So it will be 27.5. That is R2 is 0.0275 meter. thermal conductivity of A is given here 20 watt per meter degree centigrade. Kb it is given, that is it is insulated 85% of magnesium, it's 0.02 watt per meter centigrade, and T2 is 300 degrees centigrade, T3 is 100 degrees centigrade. The heat loss per meter length Q upon L it is given. The allowable heat loss per pipe is 600 watt per meter. So Q upon L is given 600. So minimum thickness of insulation R3 minus R2. This is R3 minus R2 is nothing but 2 minus 3, which is given as Q is equal to 2 pi L T1 minus T2 divided by ln R2 upon R1 upon K, which is equal to 2 pi L T2 minus T3 upon ln R3 upon R2 upon KB. Now Q upon L is given to us. So take L to left hand side, Q upon L. This equation will be as it is, omitting L only. Q upon L is 600. The first question, minimum thickness of insulation, means we have to determine here R3. So equate 600 and this, we will get R3 as 1.0427, that is 0.0287 meter, that is 28.7 mm, that is 1.2 mm. R3 minus R2, 1.3 mm. This is the first answer. Second question is the temperature of inside surface. T1 we have to determine. So compare 600 and this, we will get and obtain T1. T1 is 300.45 degrees centigrade. Thank you. Thank you very much.